will start our colloquium today. So before the Professor Yang giving this colloquium, I will just have a brief introduction to what is President Yang. Okay. Professor Yang graduated from National Taiwan Normal University in 1978, and he went to Iowa State University to pursue his higher education, and he obtained the PhD in 1987. Right. So after obtaining his doctoral degree, then he went back to National ASIAA University as an associate professor. Then after that, he became a professor and became the Dean of College of Science. And also too long. Sorry, I just named something very important. Okay, in 2001 and to 2004, he is the director of the science division of the National Science Council. Then he became the deputy minister of the NSC. Then after that turn, he became the president of National ASIAA University. Okay, he is actually the first minister of most, starting from 2016 to 2017. Okay. So there's a lot of things. So anyway, his expertise is actually experimental physics on this superconductor. So let's welcome Professor Yang.
Thank you, Professor Yang. 大家午安，大家好。First of all, I would thank Dr. Chen Wei-Ting. He invited me to be here for this colloquium. In fact, I tried many times to visit his lab for the collaboration with high pressure synthesized sample or a grow single crystal with Zhou Fangzhen. Anyway, this is not my original thought for the title. And just last month, right, of the paper published in Nature called Room Temperature Superconductivity in Carbon Sulfide Hydride. And soon after, I was asked by somebody, many people said, is it possible to get Nobel Prize? Well, a very typical question. Maybe you can ask yourself and then you answer yourself. And I just provide some of the story I know in the past maybe 20 or 30 years. And some information help you to judge somebody will get the Nobel Prize. Okay, so I'll give you several unique phenomena of superconductivity and the history, the search for new superconductor before 1986. 1986 is a critical time for the development of superconductivity. Okay, the first unique property for superconductivity is so-called zero resistance. So really interesting in 90 discover for the to discover the mercury in about 4.2 go to superconducting transition. And this is in 1911, and soon after he got a Nobel Prize. I cannot. Okay, so once you know this zero resistance will be many applications, right? The first one is electricity transmission line. If you don't have zero, it's a resistance, then no heating, so save energy. And from the Ampere's law, if you have a high zero resistance, you get higher electric current, then you create a high magnetic field, right? So this is some application to you need a high magnetic field, like NMR. So zero resistance give you many thinkable applications. Hopefully this one. This is nowhere.这个方向是吧？
应该是看这个，就是键盘拿这个图标。
键盘在哪里？不然用这个，这个好像刚才有地方。
这个还没有，真的了解一下。
Okay, so this is fourth Nobel Prize get the Nobel Prize from superconductivity field. Okay, the second unique property for superconductivity is called perfect diamagnetism and flux exclusion. That means if whenever you cool down the material below critical temperature, or you apply field and cool down, finally the flux will exclude from the material. Okay, so we call diamagnetic and flux exclusion. Sorry. And this flux exclusion, you can stick up the application for like a flux repulsion variation. And very recently, it's a high-speed magnet trap. Okay, this is from the second unique property from we call Meissner, but I didn't find Meissner get Nobel Prize. Should be right. So important discovery and mass application, but he didn't. The third one for unique superconductivity is Josephson effect, right? It's S junction and the micro bridge. You get a Josephson effect. This is discovered 1960 because this so sensitive of testing for small magnetic signal. So, and see. The most popular we can see is so-called squid magnetometer. Okay, this is a small, very sensitive signal detector. So these three important, unique superconductivity. I think if you get one of two or three, then for sure it's a superconductivity. So nothing else. Physical property have this property. So you got Nobel Prize in 1973. Huh?
He was only 7 years old. Very young, but he was
Very young, yeah, 1940. It's about 33 years. At that time, it's almost the youngest, right? 30 years old.
Well, he did that when he was a graduate student. And then he moved on to do brain science.
Yeah. Unfortunately, he didn't go to Wall Street. Okay, so you can see the problem application for high, I say the high DC. So see this application is related to the zero resistance, Mason effect, and then Josephson effect, right? So from energy, transportation, communication, because later on they find superconductor have an energy gap. So some of the function like a semiconductor can be realized like in superconductor, because energy gap is about 3 order magnitude of a semiconductor. So speed, maybe sensitivity higher. And because higher magnetic magnet can do something even for high energy accelerator. Okay, I'm not sure if this can be realized in room temperature. Then may change part of the science technology in the world here, right? Especially for industry. Okay, so that's why superconducting is many people expect very high. Okay, from research point of view, they have 3 major parts: superconducting material, device, this application, and most of the like us and check physical property and the theory to explain the superconductivity property. Okay, I would say this is the most exciting to look for new superconductor, right? Easy, and then everybody knows it. Okay, so after mercury has been discovered, then many people just go through all the periodic table, right, to find possibly higher TC and HC2. And I would say, so finally, the higher TC is niobium, and this is what? It's 41 here. TC is 9.2. HC2, SC or HC2 is 9,982 gauss. So it's not large enough for what TC is not high enough to be applied for. And every time you have to cool down by liquid helium, right? Okay, I would say this red color is superconducting at ambient pressure, and some of the elements have to be at a high pressure to be to make the superconducting occur. Okay, this is my thought. If we look going to most of the physical developments, you have experimental discovery or theoretical prediction, and then back and forth, right? But for superconducting material discovery, is totally not the case. So once you have a new superconductor, you try to find new mechanism, but they didn't give you any help to find new superconductor. And new one can be explained by new mechanism. Okay, this is the kind of model of development superconductor. So at some period, theoretical people don't talk too much with experimentalists because not many help. Okay, so that's why I say, okay, even most of the new superconductor discoveries by accidentally. Okay, I list them down very quickly to here. Before 1957, they have 2 material. I was just this niobium, titanium, TC is 10, and SC2 is 11. And number 13, TC is 18K, S2. So if you see the superconducting magnet below 10 Tesla is using this superconducting magnet, using this material. 14 Tesla uses this one. Okay, so this is still most commonly used superconducting magnetic wire for this one. So this is still good. And if I say something wrong, somebody can just correct. Before 1957, not many people don't understand what's going on for the occurrence of zero resistance, right? That means zero resistance cannot very successfully explained by physical mechanism before 1957. And this is BCS, right? 1957. They have a Cooper pair, established Cooper pair, and isotopic energy gap. They established so-called microscopic serial superconductivity. Okay, somebody may have good to explain that. I'm not going into detail about that. And this is the paper, 1957. I just go to search the citation, 8,519 times. Okay, maybe this is some criteria for if you can judge who is going to get a Nobel Prize. Okay, but anyway, BCS, he's a professor and postdoc and PhD students, right? This is Bobby is get second times Nobel Prize. Okay, unfortunately, the BCS theory predict, because they have a isotopic pair or electron-photon interaction by temperature right in the formula. So they predict from BCS theory, the TC limit is about 35 Kelvin. If we want to, okay, I just say, even those Nobel Prize prediction, somebody don't believe it, right? Okay, so if you want to go to higher than 35 Kelvin, then maybe you need a superconductor beyond BCS. That means BCS cannot explain your physical property. Or you aim to find TC higher than 77, then you should get Nobel Prize. So this is a dream for us. Okay, this is after 1972. Okay, and after 1972, so they have some intermetallic compound like a binary and toluene comes off, especially for this one, as it's the highest the record in 1973. And just as I told you, many people try to find some other superconductor beyond BCS. This is the one. Because this toluene is magnetic. Chain is in this period. 1977 from San Diego. Chain school. This superconductor, magnetic superconductor, is explained by BCS. This is the cycle time. And later on, this another superconductor called a heavy fermion superconductor cannot successfully explain BCS. 1979 from Germany. Cited 1,570 times. So at least these two can at that time just before we studied for PhD. And the same time, 1978, another paper. This is Zhu Jingwu. He published a paper called let me put it another. A diamagnetic anomaly about 90K over temperature of this one. He just said a diamagnetic anomaly 90K. So it's just flying over the 77 Kelvin. It's a big news, I think, because at 78, this view in Taiwan. Another 1980, 77K. Okay, this should be made a good news at that time, because almost 70, flying 77 should be get Nobel Prize if this is true, right? But if you look at the citation, it's quite low. That means the development of this superconductor is not good as expected. And I said at this period, just find me going to United States for study PhD. 3 years increase 1K. So it's no hole, right? It's so poor. I mean 77 right here. If you plot the linear one, it's going to 22 century. Okay. Here you need a liquid helium to cool down the system. At least 1 liter, $807. If come over here, it's 1 liter of liquid nitrogen is $15, right? It's even cheaper than mineral water. So this is a dream, I think. This is a dream. Okay. Well, if you don't believe, or you believe something happened right here after 1986. Okay, I give you some of paper. 1986, one paper published applied physics later. Superconductivity now whatever, 44 Kelvin. You see, if this is a department in electronic faculty of engineering, I'm not say something, but you see the temperature. Not in physics, no people get this from high temperature to low temperature, right? So it's, I think maybe he submitted to PI and then slowed it down. Okay, cited 8 times, so it means nobody can be confused. Okay, and this is the time of 1986 is the booming age. Okay, the paper called high DC superconductor in this one, 1986, April 7. Unconfirmed stories that this paper go to physical rehabilitator and then rejected. And he submitted to Z-Physics. It's a German journal, maybe impact factor less than 1. Okay, and he had to ask him to, if you want put the possible, and then I accept it for publication. Okay, 30 Kelvin. Luckily, not much, about half a year later, Pro Chu in Houston said, evidence of superconductivity of 40 Kelvin. Published 50 later in January, okay. It's cited 1,287. I would just tell you how competitive of this research at that period. December 15 here. So it's about 1.5 months for publication. This is 26. Okay, and soon after, this People's Daily News is 中国的人民日报 just news, not a paper. 发现了70 K 的 it's amazing. Everybody who try to get involved because it possibly to be a Nobel Prize winner. Okay, I just wanted to just about half months later, Barrett people cover this is typical people. Publish the paper is the same volume, January 26, but it's just about 2. You see, this one is less than 1 month. That means just 2 weeks later they submit a paper to yeah. But they just 2 weeks, Barrett can make everything clear. Composition, TC, everything. 2 weeks after Fortune's paper. And this is even amazing. March. This is 87 already. 87 March. The publication for 93 K. from MKU and Fortune School. Everybody know. Now he is already studied 5,000, 3 times 79. This last week and 2 weeks ago. Oh, sorry about. Oh, I have to give the very important signal here. See, Fortune finds 30 Kelvin. He go to applied pressure every time. Go to applied pressure from 30 to 40. That means pressure effect did, in some case, the enhanced superconductivity. Okay. And I would guess, I didn't find the paper, maybe some other paper. He didn't apply this one. And in fact, applied pressure decreased the TC for 1237. You see that I guess the chair maybe agree with me because 30 Kelvin is a national. Applied pressure enhanced TC, so you are eligible to replace national by yttrium. Right? This is a very important signal to get this one. See, almost the same composition, same material, but just replace national by yttrium. So you get a higher TC. Okay, the time is here. March 2nd, and well, but just 3 days later, Belgrade people, March 5th, submit another paper. Okay, just 3 days later, he can do everything. 1, 2, 3, TC, and every superconductivity parameter. Just 3 days enough for Belgrade to reproduce your result, and even better. Okay, now the citation is 1,000. Okay, this is Soviet Union news. They found what, 250? Just news, no paper. Okay, because they said future Nobel Prize might be awarded. I tell you the story about how strong competitor of the barrier and the Fortune. Here is yttrium here, copper, barium. Important is ytterbium here. Ytterbium is a kind of a rare earth here, the same role. So science published a news called Why B or Not B. The story, I maybe unconfirmed the story, okay? Fortune submitted the original paper. Should be YBCO, but he put the manuscript in the YB. And Belgrade people cannot reproduce. Too close. Penalty, so some people are not showing their most adult behavior. Adult behavior. Another is small people. And this Richard Green from IBM. He said, frankly, if I had been chosen, I would not have been even put the compound in my paper until its publication. Okay, this means IBM support Fortune to against Barron. And Fortune said it was a typographical error. I'm not the true story. Okay, this is a Belgrade paper to figure out the structure. Say, okay, if you can make more copper oxide layer, then you can increase TC. Okay, so many people just, catalyst or different temperature synthesis or many other things. So the paper, see, published 240. Not many citations. In fact, this is JT chair is a Chen Wei. I'm not sure is the Wednesday. It's Taiwanese. just inverse Josephson effect.
Is that the reason why Bell Lab got the patent in the end?
I don't know.
I mean, after more than 10 years fighting, Bell Lab got the patent for ITC.
Fighting with Alabama? You mean vitamin BCO, right?
Yeah.
Okay, there's another paper, 155, 263. This is Wang Zhaoyun. You might know him, right? He's passed away.
That's right.
Okay. 230, 59 in the Nature. Please see here. I would say you can judge from the citation. Some citations increase means big effect, and less citation maybe somebody cannot reproduce. Just stop somewhere. Okay. So who were the Nobel Prize winner in 1987? Who is that? This one, possible high TC, get one. Now cited 10,484 times. Okay, these two guys, professor, and this post should be postdoc, right? In the Jewish. So higher TC is not guarantee you get a Nobel Prize. Initiation may be very important,
Yeah.
right? Initiation.
Can I ask a question? But you just showed these two publications. One is from the Japanese. No, they have the 40.
You mean applied physics later?
Yeah, no, it's I don't know if it's.
The
applied
Albion
physics
one.
related.
Huh?
Yes, it's 40 and 40K.
Outside.
Right. The other one is also roughly 40K, but the citation is much higher. I mean the Japanese, the Americans one. So why
before 86?
It's before 86.
Oh, okay.
But why the citation is just 8?
Because nobody can reproduce. You mean APL, right? APL paper cannot reproduce. Our lab try to reproduce, cannot get it for the film. But they might some of our initiation or give some idea for oxide. Okay, he might contribute some part of later research. Okay, so still even the Nobel Prize has been awarded, but somebody aimed to long temperature superconductor, right? And also high TC superconductivity. I think this is very important for after 86 or 87. Nobel Prize 87. Okay, so higher than room temperature. There are paper 588 in Finland. Side A types, just one thing. You can see this one. And business from a Purdue school, 540 times. See, the Purdue always apply the pressure, but decrease it. But this business 1112 is realized. Okay. And thallium 363 times. And the 93, another paper in the Nature for group 2. Superconductivity about 150 in the mercury 1 to 3. Okay. Very important, he applied the pressure from 135 to enhance to 150. That's why I very, very high for to always apply the pressure. So pressure is very important key to no matter go for high TC superconductor. Okay, how about the theory? High temperature superconductor theory, because everybody knows that BCS predicts 35, now already beyond 35. Since BCS is not working. So this is a representative of the theory paper by Anderson. He called RVP theory. Okay, so I'm not going to detail. He just look at this phase diagram and create some of theory. That see the citation, 6,000 times. And another PIL paper at 1,000 times. Okay, so that's
Many series.
many theories. So each series can propose several models, right? Okay. Okay. But anyway, you see, unfortunately, we just heard the news that he passed away March this week. So if we have to go to high TC superconductor, there's just no chance. But anyway, he got a Nobel Prize in 1977 for, I think, the localization. Okay, and you know, look at high TC, or you find any other material beyond PCS, or can be explained by existing theory. This is the one. Carbon 60 is very famous at that time for chemistry. Okay, got Nobel Prize, right? So carbon 60 doping potassium. This is the paper. 2060s, 80 times. Because it is like a polymer, so people just expect to expand the long chain of polymer to enhance the TC, but not develop as expected. Because the carbon here, and then somebody put a carbon here. Try anything new discovery and many follow. Okay, this is the paper PIL, 60-70 times. And this is another different kind of material, so-called superconductor in layer perovskite without copper. Instead, it's a social lucid. Cited 900, 1,090. Because this is has been studied a lot, because this might be the so-called P-wave superconductor. BCS is the S-wave. This is so-called P-wave. Okay. And this one, this is unexpected, MGB2 from Japan. This is intermetallic without copper, without oxide. So this can be like this one, be more application to be expected. This is a paper, Nature, 5,000 times. People try to look at, uncle or aunt, just his brother, but didn't get anything. Just MGB2 is just one, nothing else nearby. But I think many people expect this very much, because intermetallic, easier to processing, easier to make application. So maybe 20-something Tesla magnet using this magnetic wire, MGB2. MGB2, B2 right here, and somebody just another MG here, 495. This is just Nature or PI, okay? And this is even interesting. Sodium cobalt, very interesting is this water molecule. Even though TC is very, this is the paper, 1,132 times. Okay, this is original compound and integrate water molecule between and make the superconductor. This is another time find ion here. In between here, high TC is most of it is copper oxide, and this ion, arsenide, okay, it's published by Japan, TIT, Hosono. Now is from chemistry, so now it's 6,000 times, 6,000 times, because later on many ion superconductors come out, so many, this one, comparable to carbon dioxide. So that's why they have so many citations. And this paper can be determined to say something because MKU here. So 2008, published in PNS for just element of the ion arsenide paper. Now it's 2,145 times. I'm not sure. This might be the most cited, one of the most cited paper in Taiwan in this year, right? You heard any paper more than 2,000 times recently in Taiwan, from Taiwan? So we have to give the NTU high appreciation. Okay, I just give me just about 1 minute. Show you how we did it in this period. We're just using low temperature specific. We set up low temperature calorimeter at high field. This is electronic, superconductor electronic. Heat capacity, we can put it down. And using this energy symmetry, we can fit in which model is better for S wave, see, S wave or D wave or P wave or S jet plus G. So we did at that time high TC, less num here in PRB, and impurity effect, the PRB 2000 and PIO to figure out the best of state 2000. And we also using numerical method to fit the possible S-wave superconductor with 2 gap. So we set up this one, and very successfully to describe MGB2 is a 2-gap superconductor. 2 gap, and then this is consistent with the other experiment or theoretical prediction. MGC NI3 is another one. Just what I show you. Nature paper, water, we did it. Even each nickel bone carbide, we also follow up. But anyway, yeah, we fit it, and this can be described by 2 gaps superconductor. Even for ion cylinder, MKU's group. And now, where to look for long-term superconductor? It's about 10 years ago, MKU invited Paul Chu and several superconductor people to Dongfa, Bali, have a workshop, a small workshop, and after that we have a coffee, dinner, and we just check where to look for temperature superconductor. Let me give you some of our thinking. We said that from civilization of human, you see a Stone Age, 石器时代, okay, and 铜器时代, copper, and iron. Now is silicon, right? How about superconductors? Mercury and carbon oxide and iron oxide, and I'm not sure where is it. And we compromise. Maybe it should be a carbon containing, right? Possible, right? Okay. That's about 2010 or 2012 in Dongfa. We just check each other after dinner. 2015 paper come out, conventional superconductivity at high pressure in sulfur hydride, right? Sulfur hydride from Germany, Max Planck. Now it's only 800 times. This may be increased very quickly, I would say. And 19 last year, the paper 260 lanthanum hydride. This is from George Washington University. US. Okay, but very high. This very high pressure. See the mega pi is about 188, so it's a mega atmosphere pressure. Looks like light years in astronomy. But it's so large, you cannot imagine. And last year, another paper, same as Germany. See the lithium hydride, so they reproduced that. So Germany reproduced the George Washington result. 250 or 260 at about the same pressure. Here they have a isotope effect. It means seems nearly to be B-set theory can explain conventional superconductivity. This is last year's paper. I mean last month's paper. Okay. 4 times. See, I just want to tell you this carbon sulfur hydrate. So carbon is very important. Let's look at that. Or hydrogen. Okay. All right, but this data is more convincing than other ones. See, the negativity and diamagnetic, magnetic field effect, and this paper looks more convincing than the other. Others just negativity, didn't find the diamagnetic effect. So this paper is more convincing. University of Rochester, US. If we go to YouTube, they have several advertised. They believe they can get Nobel Prize. Try to advise. Advise. Okay, I summarize Nobel Prize winners: 1993 material, 72 theory, 73 physical properties, Josephson Johnson, 87 material. 2003 is another theoretical for type 2 superconductor theory. And I'm not sure it's a room temperature material or high TC superconductor theory. 2021. And okay, let's get it. I just propose. You might get your answer yourself. First of all, I propose YBCO because for Chu and Kevin, right? But anyway, I judge this by criteria if the paper cited more than 5,000 times. Okay, this 6,000 times. TC is just flying over 77 km. May have a chance, right? And MGP2, 60,000 times. I'm not sure somebody else can follow up this one to get intermetallic superconductor with high TC than 77, other than oxide. There might be applications everywhere, so this is possible. And this ion, right, 60,000 times. I'm not sure these three, which one can get it, but very similar. Very similar. And I would give Paul Chu extremely credit. High TC induced or enhanced superconductivity. I think he should be recognized the world initiator. High TC will enhance or induce superconductivity. Okay, I'm not sure high TC superconductivity because Anderson is just was passed away. Who will represent the theory to get high TC? Okay, that's my talk. You can judge yourself who is going to get Nobel Prize or not get it. Thank you very much.
Okay, do you have any historical questions?
If we want to apply high pressure to increase TC, how large is the pressure will be practical?
We have a pressure cell in Taiwan. Typically is this is about 200 gigapascal. We in our level 2 gigapascal. So it's about 100 times less. If we can enhance or induce, I think you can see the signal at very low temperature, very low pressure. See, even for the one here, or here, low pressure is already induced. But this several high pressure one is a 100 gigapascal scale. We just 2 giga, about 100 times less. This is because this is a diamond emulsion. If diamond emulsion like, that's why I try to correlate with weighting. Weighting, you can make the sample at high pressure to 100 gigapascal, right? 10 gigapascal. Another I expect is to synthesize a sample at high pressure and get the superconductivity at ambient pressure. Then you get Nobel Prize. Right? If this one, this is a gas or sapphire in here, you apply pressure, you get superconductivity. Why not? Just, I'm not sure something, to synthesize at high pressure and get it out, stabilize, quench, or whatever technique to measure superconductivity at ambient pressure. Room temperature, you get Nobel Prize. This one, even beyond this one, right? If you get it, this just throw away. Am I right? So we get a chance. We get a chance to synthesize the samples at high pressure. If you get to measure the zero resistance at ambient pressure, then that's big breakthrough. And more apply. Right? There's no application so far. Just science. So if you look at it, it's just science. Maybe you have to wait to stabilize an ambient pressure or application. Once you get you synthesize the samples at high pressure and get it out and stabilize and measure at high TC, close room temperature or close somewhere. You will get Nobel Prize.
Is it necessary or how to write down the Hamiltonian or derive the Hamiltonian to find the ground state eigenvalues in the long range order?
Okay, that's beyond I can answer. I'm not sure somebody can answer it.
I mean the Hamiltonian or derive the Hamiltonian.
Yeah,
necessary to write down.
I just mentioned this is about 3 parts. Material and superconducting and another theory, or whatever, just what you say. If we want to get Nobel Prize for high theory, then the people can answer your question. Theory, right? Sorry about that. I can make.
First, I will make a joke made by Professor Guang Weiyan. He said how to find a room temperature superconductor. Maybe I can just say in Mandarin. 他说，如果你要找一个室温超导体，你就拿一个磁铁去升上，然后看哪个东西被它排斥due to the Manson effect. Then you find a room temperature superconductor at ambient pressure. That's just a joke. Okay.
Even this is a joke. You know, Portugal told at least NS support one or two group to search high TC in National Geographic geology museum in Washington, D.C. He tried to get more than 1,000 or 10,000 or 20,000 mineral to take a look. Because high pressure and high temperature might come from the mineral. Even you go to volcanoes or get something.
Yeah, just get a magnet and see
I'm
what
not
can
sure.
be.
They might some more idea about that. So one group NSF supported to look for all the mineral in the National Geology Museum in Washington, D.C. They were one group to do that.
Okay. Actually, I have one question about your work. So you mentioned
Not my
about
work.
no, your work. You mentioned about the S way, D way, P way, with the gap as a function of some cosine, sine, theta. So what define that direction, the theta, which orientation?
Yeah, that's the question. So we try to use a single crystal to fit in different direction.
Yeah, but theoretically, what define that angle? Yeah. I mean, your energy gap is a function of some angle, right?
Yeah. Anyway, in single crystal you can turn different angles. Magnetic field you can turn different angles to verify that. Very early is崔章启院士. He did a lot of this very tiny work. We just specifically is more or less is a bulk property. It's not that sensitive to direction. But for the tunneling, his technique is very sensitive to different direction, even from momentum space, different angle. He did it very thorough.
Has anyone looked at the variation of the critical temperature versus pressure?
What material?
The pressure dependence of the critical temperature in this type
This one?
superconductor.
This is critical temperature.
I know, but
What?
if you vary the pressure,
This is under pressure.
I know that's the thing. So can you plot the curve?
Yeah, curve like
Shows
here,
the-
80 Tesla.
Oh, okay.
But this rather too less point here. But use a WHSS series or something to do plot about 80 Tesla. So that's what I say is a more convincing data. They can magnetic field effect and diamagnetic and see. If we go to supplementary, the paper of supplementary, more than 20 times they try. That's why many people believe it. Supplementary many times data.
You talking about using pressure to tune the TC, but another factor you can do is dimensionality. You mentioned the iron selenide discovered by MK, but people put the monolayer iron selenide on top of strontium titan, and TC increased by 20 or something, 40. Any idea what's the reason for that?
Early stage, low dimensionality is it favor higher TC, right? So that's lower dimension to get higher TC. Even for HC2 is increased, enhanced by lower dimensionality. So same field is better higher TC. So that's why I say Japanese, China people make a lot of different structure of iron selenide, iron oxide, but they increase the TC. MKU TC is about 6 or 7.
Yeah.
6 or 7, but that's 6 or 7. A K1, right? A K1.
Yeah,
But I think Chinese scientists going to 60 or 50.
I mean, roughly, I did not follow the literature. Any understanding about why going from 3-dimensional to 2-dimensional TC increase?
Right. This one has been studied mainly in cubic carbon because layer is a favor higher TC.
I see.
Then they have, I think that the theory has been very mature for lower dimensionality increased TC. But so that's why so many people just have 1 layer, 2 layer carbon dioxide can be superconductor or not.
Thank you.
Thank you, Professor, for those. So I have 2 questions. The first question is like from one of the slides, you shows like a periodic table, and from the periodic table you show that some of them might exhibit some kind of superconductivity at different temperature. But also in that table, it seems like there are some metals that you don't really label it, like the silver.
Yeah, it seems to me it's not that correct so far.
So
that's a very old data.
So just my question is like those, like let's say there are some metals. So some metal you don't really observe it, or just that it can't be superconductive. It can't exhibit the properties. Is it either we haven't observed it yet, or it just can't exhibit the property?
Because periodic may be made very early. So like copper, silver, and gold is a good conductor, but it's not a good superconductor. At least go to micro Kelvin, they don't see it. So they may give you some idea. Superconductivity is not extended good conductor only. Right? Good conductor cannot make sure to be superconducting. Right? So electron phonon interaction may be another key to form the superconductivity. Since copper, silver, gold is most popular good conductor, but at least go to micro Kelvin.
And then the second question is like from like all the experimental structures of the superconducting material, it seems like the combinations of the metal are kind of random, I would say. So it's like how you actually do it? You just like take random combinations of metal and then you try your luck to find it, or is there some kind of theoretical justification behind it? Like tell you that okay, for example, some metals that might exhibit like better properties or some don't. It's like, how do you do it? It seems like quite random. It's like you just compare metal and
That's a good question. It seems to me the young people have more chance to it. I told you the model of the development of superconducting experience was theoretical guiding, make any help.
Can I make a comment? Can I make a comment? Can you show this hydride nature paper?
Hydride nature paper?
Yeah. This one, yeah. Actually, if you look at the paper carefully, it said that why they're working on this because that one was predicted by first principle calculation.
Okay.
Yeah, I'm referring 14.
But I mean, to look for the new superconductor or high temperature, go to lithium or hydrogen. Very light element is common sense at that time.
Yeah, this one probably unique one. You go predict first and then synthesize.
What is the origin of the high pressure mechanism? Origin of superconductivity?
Not yet.
The origin, not yet. No.
Not yet understood. Because even under high pressure, the material structure, anything is not yet understood at the high pressure. See, it's conventional. Conventional means looks like a BCS theory. So, yeah, phonon mechanism. So at high pressure, because I mean the BCS predict the 35 Kelvin is at ambient pressure. So at high pressure, maybe the material vibrates so high at the high temperature or something, right? At ambient pressure, they just broken. Otherwise, how to describe this high TC?
I think at that time that's called weak BCF theory. Now this is in the strong coupling BCF theory.
Okay.
So anyone else?
Okay, so theoretical people can make some more.
Yeah, I said predict before they do experiment.
Yeah, once you predict another material, just tell us to try, right? Once you predict before publication, just ask us to try.
This experimental honest to say that why they're working on this system because it was predict. If we read the paper, it was say.
And if we get Nobel Prize, the theory people can.
Well, I'm not sure. Experimental physics. Isn't it? You say that the paper published, if not confirmed, they're just forgotten.
But I think the young people have a chance to do it.
Okay. If there's no other questions, let's thank the Professor Yang again.